Hello, this is Mr. Gilmore with the 8.7 applications lesson. Now, this is going to be an application lesson involving our sine, cosine, and tangent functions. However, we're going to see them in a different light. We're going to actually apply them with some familiar triangles that we have encountered in the past, and we'll actually look at what are some other things that we can use these trig relationships with. So let's start with something familiar. Let's go back to our 45, 45, 90. Now, in the 45, 45, 90, remember that what we proved was that the three sides of the triangle actually have a unique ratio to them of a 1 to 1 to root 2. Now, what we can do then is we can take our special right triangle, our 45, 45, 90, and mash it together with the sine, cosine, and tangent functions. So now let's do some investigations, such as what is the sine of 45 degrees, what's the cosine of 45 degrees, and what's the tangent of 45 degrees. Now, I've already got a diagram here set up of a special right triangle. Now, what you'll notice is that I have actually strategically labeled the hypotenuse of a length of 1. Now, I did that because you're going to notice that once we have the hypotenuse length of 1, it actually cleans up our sine, cosine, and tangent functions a little bit. Now, before we move on to that, though, we are going to need to fill in the remaining sides of our triangle. Now, remember, the ratio is 1 to 1 to root 2. But now that we've made the hypotenuse a length of 1, that means the other two sides must be 1 over the root 2, which then when we simplify and rationalize, we end up with this fraction here, root 2 over 2. And the legs are actually equal to each other, which means we end up with the fraction root 2 over 2 and root 2 over 2. So what this is really saying then is we can now apply our sine, cosine, and tangent functions. So think SOHCAHTOA. So sine of 45 is the opposite over the hypotenuse. Notice then that the hypotenuse is a length of 1. So really the sine of 45 degrees is really just the opposite side. Because we take the opposite divided by 1, it's just simply still going to be the opposite. So the sine of 45 degrees is then simply root 2 over 2. Let's apply the cosine. The cosine of 45 degrees is our adjacent side over the hypotenuse. Now, the hypotenuse, again, is a length of 1, which then means, really, the cosine of 45 is just the adjacent side, or in other words, root 2 over 2. Now for the fun one, tangent of 45 degrees. Tangent is our opposite over adjacent. Now, since our legs are equal in this triangle, what we're really doing is then taking root 2 over 2 divided by root 2 over 2, and any value divided by itself is actually just then simply 1. And so the tangent of 45 degrees is actually a length of, or is that the ratio of 1, because our legs happen to be equal. Let's then take our sine, cosine, tangent, and let's mash it up with our other special right triangle of 30, 60, 90. Now, in the example we're about to do, I've actually just narrowed it down to the sine, cosine, and tangent of 60 degrees. Now, however, on the worksheet, you will encounter the sine, cosine, and tangent of 30 degrees. Now, you'll still use the same triangle and the same ratios of sides. However, you'll approach it in a different sense from the perspective of the 30-degree angle. We're going to do it from the perspective of the 60-degree angle for this example. Now, once again, I have strategically labeled the hypotenuse of our 30, 60, 90 as a length of 1. You're going to see how that makes our calculations a bit nicer for our sine and cosine values. Now, for the side lengths of our special right triangle here, remember the ratio of our sides was 1 to root 3 to 2. Well, now that we've actually made then the hypotenuse a length of 1, we can actually then use our same relationships of the ratios of sides to fill in the missing side measures. So down here, when we move backward from our hypotenuse to our short leg, we get a fraction of 1/2. So the length of our short leg would be 1/2. Then moving on to the long leg, we simply just multiply our short leg by root 3, and we get the fraction root 3 over 2. And so what we're doing there is now we've filled in the missing measures of our sides. And again, letting the hypotenuse be a length of 1 is a bit of strategy on our part. So let's do the sine of 60 degrees. Well, the sine again, SOHCAHTOA, so is opposite over hypotenuse. So the opposite is root 3 over 2, and our hypotenuse is 1. Well, we divide anything by 1, and it is itself, which means simply the sine of 60 is root 3 over 2. Now let's apply the cosine of 60. Cosine is the adjacent leg over the hypotenuse. So we move to the adjacent side, which is our 1/2 over the hypotenuse of 1. Again, divided by 1 doesn't change anything. So we simply then have a ratio of 1/2 with our cosine of 60. And then the tangent of 60, this is where it gets interesting, is our opposite over hypotenuse. Or sorry, opposite over adjacent, which then means we're taking the root 3 over 2 divided by 1/2. Now, another way of thinking about it is we're actually can divide the fraction, so we flip and multiply. What this is simply simplifies down to is just √3. And so there we have it, the tangent of 60. Now, of course, again, on the worksheet, you're also going to explore the sine of 30, cosine of 30, and the tangent of 30, and you'll use the same triangle here, just from the perspective of the 30-degree angle. Now, another thing we can do with our trig ratios, and this is where this one is actually kind of a fun game. This is called the all given one scenario. What that means is you're going to be given one of the trig ratios. As it turns out, if you're given one of those trig ratios, you can actually find all of the trig ratios. So triangle ABC is right with its right angle at C. Find the cosine of A and the tangent of B if the sine of sine of A is 2/5. Now, this sine of A over 2/5, that's our key into figuring out what our cosine of A is and our tangent of B is. So where are we going to proceed with this? Well, think about what it means to be sine of an angle. That means the opposite side and the hypotenuse side must form a ratio of 2/5, right? That's what this is saying. The sine of angle A is equal to 2/5, angle A being an acute angle. So what we can do with our statement is we can build a triangle out of it. So let's actually construct our triangle ABC with our right angle at side C. And what we're saying is from the perspective of angle A, so if we are in this angle, the position here, we're looking at the opposite side and the hypotenuse making a ratio of 2/5, simply meaning we can just attach our value 2 and 5 to the side lengths. And what we have there then is a triangle with the sine of alpha being the ratio of 2/5. But we know more about this triangle because we're given then the ratio of those two sides, which then means we can find the ratio of the third side by applying the Pythagorean theorem. So what we're doing then is we are going to fill in this missing blank of a side here using PT. So now let's go ahead and fill that in. I'm going to call that side lowercase b. So let's look at for lowercase b. So we've got 2 squared plus b squared is equal to 5 squared. Let's go ahead and evaluate this and solve for our b value. So I get 4 plus b squared equals 25. Subtract 4 on both sides. We get b squared equals 21. Then take the root of both sides. We get simplified to b is √21. So let's go ahead and fill in that missing side as √21. And now we can actually find the cosine of angle A and the tangent of angle B because we have the proper ratios of the three sides of this triangle. So let's do the cosine of angle A first. So the cosine of angle A, right, would be the adjacent over the hypotenuse. So the adjacent side to our angle A would be √21, and the hypotenuse is 5. So there's our first ratio. Now let's do the tangent of angle B. So tangent of angle B is opposite over adjacent. So the opposite is √21 over 2. And there we have it. We can find these missing sine and cosine cosine and tangent ratios by building a triangle using the given ratio. Now, of course, we don't even have to stop there. We can keep going. What if I wanted to know, so we've got the sine of angle A and the cosine of angle A. What if I wanted to know the tangent of angle A? Well, I can do that as well. Tangent of angle A is the opposite over adjacent. So that would be 2 over √21. Now, of course, we want to rationalize that. And when we do, we'd end up with this expression here, 2 times √21 over 21. I can keep going. I could do the sine of angle B. Sine is opposite over hypotenuse, so we get a ratio of √21 over 5. And I could even do, I've got 1, 2, 3, 4, 5. Oh, I found them all. Yeah. So with that, we can actually find all of, oh no, I didn't find them all. We have 1, 2, I've got sine of angle A, cosine of angle A, tangent of angle B. I'm missing cosine of angle B. Let's do that. Cosine of angle B. I can even find that one. So the cosine of angle B is the adjacent over the hypotenuse, and there we have it. We can actually find all of the trig ratios given 1. And so that's the story we have with this game, as we title it appropriately, all given 1. And you're going to do something similar like this on your homework assignment. Now, the last two slides, I want to talk about some interesting things that we can actually prove as far as the relationships go with our sine, cosine, and tangent functions. One thing that we can prove is that the tangent of a given angle, so tangent of alpha, is actually equal to the sine of alpha divided by the cosine of alpha. Now, I'm going to let you prove this one on your own, but I am going to give you a little bit of advice to begin with. The first thing in your proof that you want to actually acknowledge is let's start with the tangent of alpha. And with our triangle given below, we have our triangle down here with our three sides labeled A, B, and C. It's really all we need. And we've also got our angle alpha labeled. From our tangent perspective, right, from angle alpha, let's go ahead and list out the ratio of tangent of alpha. The ratio of tangent of alpha is opposite over adjacent. In other words, A over B. So what you're going to then lean into is there another way that we can actually express our A value of our side of our triangle and another way that we can express our B value of the side of the triangle? And really the question is, how is side A and side B related to the sine of alpha and the cosine of alpha? Because if you find that, then that's going to be popped in directly into your ratio of A over B. So let that be a clue of you proving this relationship that tangent has with sine and cosine. That is, that tangent of our angle alpha is equal to the sine of angle alpha divided by the cosine of angle alpha. And there's also one more relationship we'll look at with our sine, cosine, and tangent functions. This one's just primarily related to our sine and cosine function. We actually like to call this one the Pythagorean identity. You'll actually see this come up in future relations, especially in pre-calculus, when you do work with your trigonometric identities as well. Now, for the Pythagorean identity, let the title of this give the clue away. We are going to prove that if you took the sine of alpha and squared its value, plus the cosine of alpha and squared that value, that you would actually sum those to equal 1. That the square of those ratios, the sum of the squares of those ratios is actually equal to 1. Again, we have the same triangle with angle alpha labeled, and we've got our three sides A, B, and C. Now, again, let the title of this be your clue. The triangle we're given is a right triangle, which means, obviously to be true, something we have been using over and over again is our Pythagorean theorem, a squared plus b squared plus c squared. Now, again, I want to prompt you with a question. Is there another way that you can represent our side A? Is there another way you can represent side B such that they are related to the trig ratios of sine and cosine? Because if that is something that you can find relationship with side A and side B in relation to sine and cosine, then use those relationships and pop them into the Pythagorean theorem and watch what unfolds. Again, I'm going to leave you guys to do this one on your own. But if you do have any questions, you can go ahead and email me about that. All right, so we've come to the end of our lesson with 8.7 on application. Please be sure to hop over and take a look at the 8.7 worksheet. And as I already said, if you do have any questions on this assignment, please don't hesitate to email me and I will get back to you. With that, be good and do good.